In this video I'm going to talk about the momentum of the wing. I'm going to look at different airfoils, what the momentum they have, and so on. And the main reason for this video is that I have seen many not very smart comments about this subject. For instance, people claim that the momentum that they get from airfoil or from somewhere else is going to influence the performance of the plane. Let's say if you have the negative momentum, the wing is stable. If you have the positive momentum, it's unstable. If you have zero momentum, then you're going to have maneuverable plane. So this is all incorrect. And let's do it in the right way. How to determine the momentum of the wing or airfoil. So the first step to get the information from airfoil. So there you have a command to get the pressure vector for each element of the airfoil, and as a result you can plot this graph. So on this graph you see the force acting on each element of the airfoil, and this force is normal to the surface of the airfoil. So the second step is to choose the point over which you're going to measure the momentum or calculate the momentum. So by convention, this point is 1/4 of the chord length. So you go here. So this is the 1/4 of the distance. But you can pick any other point. So any of the point is good. So once you have chosen the point, what you do, you just plot a vector to each element of the surface. Then you plot a normal to this vector, and then you project the force onto this normal. And once this is done, you have the force and you have the distance that you need. And here's the equation for the momentum. So in that case, force is just in a way singular force, but in this example we have distributed force. So on each element we have the force acting, so that we have that's why we have distribution of the force of the surface of airfoil, or the line of the airfoil. So we introduce this distribution with Q, defines distribution, and then what we do, we compute the momentum usual way. So you have to integrate over each element. So basically you have this vector going to each point of the airfoil, and this point you calculate the projection of distribution of force onto the normal to this vector, and build this for the whole surface. Pretty simple. But what we do, we will split this airfoil into two sections. It's easy to calculate, and you have more insight into what's going on. So we split this into two sections. So the one section is a section before the point at which we measure momentum, and second section is up to this point. And we also, what we do, first we just use some toy model. So let's say we have this toy model. I have force distribution, basically a linear curve, which increases from the tail to the nose linearly. So you basically don't have this fancy shape, but you have just straight line going there. So we have this toy model. We split this model. We split this curve into two. So first section is the tail section, and second section is the nose section. And we choose a point. I define this point x equal t point. So not this point, 1/4 of the chord, but any point. So once we have done this, what we can do, we can calculate the momentum from the tail and from the nose separately. So again, this basic equation for the calculation. So you calculate momentum here, basically going to each point there and getting the momentum, and then summing the small pieces of this momentum to the complete sum. And the same is for the nose section. And you do this for each point. So the t goes from 0 to 1. So basically do it for this point, for that, and so on. And as a result, you will get at each point of the airfoil two numbers. One number is blue, and second number is red. And you can plot the curve. I have done this already. So So basically we're going to have two curves, the red curve and the blue curve. So the red curve corresponds to the nose section and the blue curve corresponds to the tail section. Okay, but I will talk about this a bit later. But now let's do the simple mathematics from the high school and define this distribution as a linear function kx. And then you integrate those integrals. So you have one integral for the tail section, one for the nose section. So you plug this inside. It's very simple, and you get actually what I'm looking for. I'm looking for the number t at which you're going to have the force acting on the tail section equal to the force acting on the nose section. And if we make those momentum equal, from here we can find the t number. So the x has to be 2 over 3 to have those two momentum equal at this distribution of the force. So basically the t is equivalent to 2 divided by 3 if we have the linear distribution of the force. And the force does not depend on and this point does not depend on the k constant for this distribution. So we can do the same for the function kx squared, get a bit different results, and the same for the kx cube, and get again different results. Okay, so this is the analytical solution, again simple solution, but what I'm interested in, I'm looking for the, actually would like to have the results for the real distribution of the force from the airfoil. So that's why I replace this analytic integral with the numerical integral done in Python. Where is my Python? Okay, so here is the numerical integration. So I introduce the q function, which is for distribution. I can have any of the function I wish. Again, I'm playing this determined model to make sure that I have the consistency. So I can plot this function, which is the function, the q function, and I can integrate the result as I have done analytically. So here's the integration routine. So I have two integrals for the tail section and the nose section, and then I can plot the results. So here's the results. So let's talk about the results. So it's a bit messy, but actually it's very simple. So the momentum acting on, so the force acting on the tail section leads to the momentum, and this momentum is going to be different depending on the point at which you are looking at this momentum. So if I plot this graph, we're going to have blue curve. So almost zero momentum. So here is my section. So almost, yeah, so this is the airfoil section, this is the force distribution acting on this airfoil. So I have different force acting on each element. And here is the graph of the momentum. So if I choose the point, let's say here, I'm going to have 2 points, blue point and the red point. Why 2? Because I have the tail section momentum and I have the nose section momentum. So I have 2 points, and I can do it for any other point on this airfoil. So this point is 1 force of the chord taken from the nose. By convention, this is the point at which the momentum is calculated. So this point is here, and if we look at the graph, so in this case I have the cubic distribution. If you look at the graph, I have the equilibrium point close to the nose. Not at this point, but somewhere there. So I have, once again, I have the blue line and I have the red line corresponding to the nose section. And I can compute the difference between those two momentum, and I get the straight line. And this is what I got in the calculation as well, so it's a bit surprising, but the difference between momentum is actually linear function. Okay, but to keep it simple, I will just say that you can do all of those things, and then probably you can just go to the conclusions. So if you look at the conclusions, so I have plotted three different distribution forces, three different functions of distribution force. So this is linear, this is quadratic, this is cubic, and what you can look at the equilibrium point. So the first case with the linear, the first graph is for the linear distribution. So you have the equilibrium point behind the point at which usually the momentum is measured. Then you have cubic, then you have quadratic distribution. For this distribution, we have exactly one force over chord taken from the nose, exactly the same as the point at which they chose it by convention. So we have the same point. And if we have a cubic distribution, then this equilibrium point moving back, moving closer to the nose. Well, so I also showed with the, so if you look only at the conventional point, so the usual point at which we measure the momentum, in that case you will see that if you have the distributed force linear, then you have the momentum acting on the tail higher than momentum from the nose. So that the wing is going to be rotating against the angle of attack, so you have basically pitch down momentum. If you have quadratic distribution, in that case you have momentum on the tail equal to momentum of the nose, and then you have exactly this point, and you have momentum equal to 0. Next, if you have a cubic distribution, so you kind of have more force on the nose. In that case, nose is winning, and the point is moving to the point of equilibrium is moving close to the nose section. Okay, and just to summarize, so if you have those toy kind of models, then if you have let's say this function, then the tail wins, and you have negative momentum or pitch down momentum. If you have this function, you have the momentum equal 0 at the point at which usually they measure the momentum. And if you have the cubic distribution, then you have momentum greater than 0, and you have pitch up momentum. Okay? And now we are ready for the important question. So the airfoil software gives us the number of momentum for different angles of attack, and this number can be different. Can be negative, can be positive. But always computed at this point, chord over 4 from the nose. So the question is, what does it mean? Is it important what this number actually is? And I believe at this point we know that it's not important. It's completely, in a way, irrelevant. It can be any number, and this number only shows us where we should place the center of gravity. So in the case we have the 0 momentum, the center of gravity has to be placed exactly chord over 4 taken from the nose. So you compute the distance by dividing the wing chord by the 4, and then you know the exact position of the center of the gravity, and if you have, let's say, momentum positive, so the nose is winning, that in that case you have to move the center of gravity closer to the nose. If you have the momentum negative or pitch down momentum, you have to move this section far away from that point, closer to the tail, further away from this point, close to the tail. Okay, so this is kind of simple, and I was surprised that you can see some confusion over the internet. Different airfoils have different distribution of pressure, and as a result you're going to have different position of the point at which you have the 0 momentum. And the only one thing you have to keep in mind is to place center of gravity exactly at this point. So if you change the angle of attack, this point is going to move probably a bit, so you just pick the operational point and pick the angle of attack that you're going to operate most of the time, and in this place you're going to choose the position at which you have the zero momentum position for the center of gravity. Okay, and the stability has nothing to do with this point. So in the worst case, if you are going to choose it in the wrong place, you're going to compensate it with with other aerodynamic surfaces, so you're going to lose efficiency, but it's not related to the stability of the plane. Okay, well, actually it's going to be a bit unstable if you're not going to place it exactly at the point where you have the zero momentum, but it's not the problem. Okay, but the stability is actually can be also connected to the momentum. So if you look at the airfoil, let's assume we have a plane and we fly at a certain angle of attack, and usually we have the positive angle of attack, and that means that if you have some perturbation in the air, you're going to try to kind of pitch up the airfoil or the wing, and it would be nice to kind of use momentum to compensate this effect. So let's say if the angle of attack is increasing by some accidents, then it's good if the momentum is going to drop, so that or becomes negative. So it's going to pull the airfoil back to the original position. So what you have to do, you have to look at this value. So you have to differentiate the momentum curve. So the momentum curve is the momentum over the alpha. Computed for each alpha, you have a certain number, the momentum, and it's good to have the negative. If you differentiate this with respect to the alpha, it's good to have the negative value of this value. I have changed the notation a bit. So the momentum is the function of alpha, angle of attack, and if you differentiate this function with respect to alpha, we're going to have this function. For the usual plane, the momentum kind of tends to increase when you increase the alpha. And for the usual plane, it's not a problem because you can compensate this with the tail on the back. But this is important for the flying wings. So if you have a flying wing, it's good to have the stable wing, so that if it's going to pitch up, you have the momentum put this wing back to the normal position. So that's why this value has to be negative or close to zero. There are a few other ways to make the wing stable, flying wing stable, or tailless airplane stable, but one of the way is to keep this value negative or close to zero. Okay, let's go to the previous results. So I have obtained in the previous section, I have tested different airfoils, cover simulation. I got this graph. So those airfoils are designed for tailless wing airplanes, and we expect them to have negative change of momentum with respect to the alpha. So we see those things on this graph. So here's the drag curve, so the drag at the high speed. So you want to have the airfoil close to zero because you would like to have small drag at high speed. And the y-axis is a lift coefficient and the small speed. So basically it defines the slowest speed at which you can fly. So you'd like to have those airfoils here. So the higher the airfoil is, the slower the plane can fly. Okay, so those are airfoils, and what I have done in this, I have modified the code a bit. So now what we have the cross mark opposing the airfoils with positive momentum. So if the airfoil has the positive momentum, total positive momentum, we have the cross side. Once again, it says nothing about the stability. It just says about where we have to place the center of gravity. So if you have the cross line, it means that you have positive momentum, so you move the center of gravity close to the nose. If it's just a dot, you have to move it closer to the tail. That's it. So we have this thing, and we can choose the airfoil. For instance, this airfoil. So here's the airfoil, and once again, so those are results for the flying wings or tailless airplanes. So we have this kind of S shape profile. So and this is done to keep this value negative. So when we increase the alpha, we would like to have the moment. We would like to have a smaller moment for the high alpha. So here is the polars. So the CL versus lift coefficient versus drag coefficient, and here is the momentum coefficient with respect to the alpha for the low Reynolds number 50K, and here's the results for the high Reynolds number, high speed 550K. Once again, those are polars, and this is the behavior of momentum measured on the quarter of the chord, so the usual conventional point. So what we see here, we see that the momentum is decaying with increase to alpha. So we increase the alpha from 0 to 4 and momentum is dropping. So this is good for stability at low speed. But if you go to the high alpha, we have this particular airfoil unstable because the momentum is increasing. So if you have some sort of pitch up disturbances, you are going to have high momentum, and this beautiful airfoil is going to flip. Not good. But you can fly this airfoil until you have like 4 degrees angle of attack. And for high speed, it's all good, because for the high speed we have this negative behavior for the momentum in a wide range, 0.5 degrees, and we need only 0.2 degrees for the operational position. So it's all good. And so except of the so what we do, we look at the curve. So it has to decay, big kind of negative inclination. But we also look at the absolute value, because the absolute value is actually important. Defines the actual force acting on the wing. So if the force is not significant, it's not going to affect the performance a lot. And what we need either to have a negative function, this function. I need a name for this function. So it has to be negative. It has to be decaying with the alpha. So go in this direction. Or we have to have it close to 0. Because if it's close to 0, then it's not going to cause any negative effects if you have some disturbances and so on. So it has to be either 0 or negative. Okay, so this is clear. So what else? Yeah, so if you have it close to 0, then it means that the plane can be highly maneuverable. If it's negative, it's going to be stable. If it's too negative, it's going to be too stable, and it's not going to be easy to control, not going to be very controllable. So, but this is not the only way to make the flying wing stable. You can also play with the shape of the wing. For instance, can have a delta shape, and so on. This is only one of the possibilities, to have this profile with this shape and to make sure that the momentum goes down with increase of alpha. And I think that's it. And probably just we are ready for picking up the best airfoil. So those airfoils are already sorted. So those having the smallest drag coefficient, for instance, PW51 is number 3 in this list. The only thing that you have to look at is to have the maximum lift coefficient that you need, because this will define the slowest speed you can fly. But I think that all airfoils with this small drag coefficient actually are good. They have sufficient sufficient lift coefficient, so you can pick any of those. And after you have chosen a particular airfoil, you can look at the, let's say we choose P51, PW51, okay? Here's the airfoil. Yeah, so this is the airfoil here, number 3. You have number 3 on the list. And if you look at the profile, it also has the S shape. Tails goes up a bit. And here is the momentum curves. For the low speed, it has nice behavior, at least well, in small range. It goes down, so you can fly it stable at small alphas at small speed, but at the high speed, it's not. At high alphas, not going to be stable. So I don't think this airfoil is a good fit for the slow flying airplanes. if you will just use it for the flying wing, let's say just the usual plane, a flying wing, not some fancy design with delta wing and so on. If you have just straight, basically wing with square kind of shape, then it's not going to be very stable because you have this growing momentum with degrees of alpha. But if you look at the high speed, it's beautiful. It's very nice curve going down, so it's going to be stable at the high speed, and you might have some issues at the low speed if you use basically board wing for this purpose. Okay, I think that's enough for today. Maybe I'll do some other video on this subject in the future.